So now, as promised, we're going to summarize our understanding of binomial coefficients in all the ways that we've studied them in these last few videos and these last few in-class activities. So we're going to review our different interpretations of n choose k. We're going to give a full explanation of the binomial coefficient interpretation of n choose k. We're going to use our interpretation of binomial coefficients to explain the formulas for n choose k. We're going to work out a counting problem involving binomial coefficients. We're going to work out a polynomial problem also including binomial coefficients. All right, so lots of stuff that we're going to do. So let's get started. So the thing to remember is there are 4 ways to interpret n choose k, and even a couple of those ways have a couple of different sub-interpretations, you could say. So let's get going. If we have a set of n elements, then n choose k is the number of subsets with k elements. If we look at bit strings of length n, it's the number of those bit strings that have weight k. If we're looking at shortest lattice paths between the point 0, 0 and k n minus k, it counts that number. And if we switch the x and y coordinates so that it's n minus k, same number. So in the expanded form of x plus y to the n, it is the coefficient of x to the k, y to the n minus k. But as we've seen, if we focus on y instead of x, it is also the coefficient of x to the n minus k times y to the k. All right, so let's consider the expansion of x plus y to the n and see if we can figure out why our binomial coefficient interpretation is correct. All right, so imagine we have x plus y multiplied out n times. So we want to find out how many times we get x to the k times y to the n minus k in the expansion. So how do we get any of those x to the k, y to the n minus k? So we choose k of those factors. There are n factors altogether. We choose k of them to get x as one of the factors when we multiply it out. And then the remaining n minus k factors of x plus y, we choose to get y as a factor. So we can actually represent each of these choices as an n-bit string. So we put a 1 in the bit string every time we choose an x. And then we put a 0 in the bit string every time we choose a y. So if we're looking at x plus y to the 5th, and let's say, I don't know, we're looking for x cubed y squared, and then this is what we choose. So we choose an x in the 1st, 4th, and 5th places, and then a y in the 2nd and 3rd. Well, the first one's an x, so we put in a 0. The next one's a y, so we put in the first one's an x, so we put in a 1, silly Darren. The next one is a y, so we put in a 0. The third one is also a y, so we put in another 0. And then the last 2 are x's, so we put 1 in the 4th one and 1 in the 5th one. So, and you can imagine doing this with every possibility of choosing 3 x's and 2 y's. You just put a 1 where you choose the x's, we put a 0 where you choose the y's. So remember, we're going to choose x a total of k times, and if we're thinking of how that works with the bit string, that means our bit strings are going to have weight k. So our bit strings of weight k, each one of those represents a different way of getting x to the k, y to the n minus k. And since our bit strings have length n and weight k, that means n choose k is going to be the number of terms that we get. And so that's going to be our coefficient as well. N choose k. All right, so that wasn't too bad. So let's see if we can work out an example. So let's suppose we want to expand 2x plus 3y to the 13th. So this is a little bit different because we have that 2 and that 3 hooked in there. So the question I want to ask is, what's the coefficient of x to the 8th, y to the 5th? Well, this is going to be done in at least a couple steps. So let's take one step at a time. So in our expansion, when we do our binomial expansion, we're going to get our first term is 2x and our second term is 3y. So we're going to get something like 2x to the k, 3y to the n minus k. Now we're going to do k equals 8, and in this case our n is equal to 13. So we're going to look at 2x to the 8th, 3y to the 5th. Now we know how our binomial coefficient works, right? It's k equals 8, n equals 13. So our coefficient of 2x to the 8th times 3y to the 5th is going to be 13, choose 8. However, that is not going to be our coefficient of x to the 8th times y to the 5th. We still have a little ways to get that. So our term is going to look like, oh, actually, we could also use 13, choose 5 if we're using y as our, using the second term as our counting. So when we combine our like terms, we're not going to get 13 choose 5 times x to the 8th times y to the 5th. We're going to get 13 choose 5 times 2x to the 8th times 3y to the 5th. So we have a little simplifying to do before we get x to the 8th times y to the 5th. So if we look at 2x to the 8th, that's going to give us 2 to the 8th times x to the 8th. If we look at that 3y to the 5th, that's going to give us 3 to the 5th y to the 5th. If we rearrange those factors a little bit, we get 13 choose 5 times 2 to the 8th times 3 to the 5th times x to the 8th times y to the 5th. And that means our coefficient of x to the 8th y to the 5th is not just that 13 choose 5, it's also 2 to the 8th times 3 to the 5th as well. All right, so now we're going to go ahead and I promised you we derived the formula for n choose k, and that's what we're going to do here before I send you off to the next problem set. So we could use any interpretation we want. I'm going to use the subset interpretation. There's a similar one for bit strings and for lattice paths. So our set is all the numbers 1 through n because we need a subset with n elements in it. That's probably the easiest one to do. And we want to find the subsets of cardinality k. Now, what we're going to do is our old strategy of counting recklessly, figuring out how we did it wrong, making corrections to make sure we do it correctly. And then we're going to clean up our errors. So, how many ways can we create a subset? So what we're going to do is we're going to set up a spot for each element in our subset, right? So what number of choices do we have? Well, we have k choices, right? K spots that we need to fill. So the first spot, a second spot, a third spot, a fourth spot, all the way to the kth spot for our subset. And I'm going to ask myself, well, how many ways can we fill in the first spot? Well, I mean, we haven't chosen anything yet, so we can choose any of the n elements for our first spot. And then for our second spot, we've already chosen one of the elements. We only have n minus 1 for the next one. For the third spot, we've already chosen 2 elements, so we only have n minus 2 choices for the third one. N minus 3 for the fourth one, all the way down to, if you figure it out, the last one's going to be, you have n minus k plus 1 choices for the very last spot in that subset with k elements. So that's our preliminary count, right? We multiply all those together to get n times n minus 1 times n minus 2 times n minus 3, all the way down to n minus k plus 1. However, we have overcounted by quite a lot. And let's see if we can figure out how. So there's our preliminary total. So let's keep that in mind as we're doing our thinking here. So imagine that we've chosen one of the subsets with k elements. So the first one is A1, the next one's A2, all the way through AK. And so whatever those numbers are. Well, if we take that very same subset and rearrange, we don't do anything with the elements that are in the subset, we just rearrange them in a different order. We're going to get the same subset. That subset will not change if we rearrange the order. However, in our preliminary total, when we were doing our counting, we do get a different subset as far as that one's considered, right? So the preliminary total thinks we're getting a new subset, but it's really the same subset. So our preliminary total is going to count each subset as many times as we can arrange the order of the subset. So what we're going to do now is count how many times we can actually rearrange the order of that subset to get an idea of how much we've actually overcounted. So our subsets have k elements, which means that there are k factorial different ways that we can arrange them, right? So if we want to arrange those k elements in order, there are k ways that we can choose the first one, k minus 1 for the second, k minus 2 for the third, all the way down to 2 times 1 for the last two. So in order to find n choose k, we take our preliminary total, but that counts each subset k factorial times. To compensate for that, we're going to divide by k factorial to get the correct number of subsets. Now, if you don't like that formula because of the dots, what we can do is we can multiply the top and bottom by n minus k factorial. When we do, that completes the factorial on top, so we end up with n factorial on the top, but then we get an extra factor of n minus k factorial on the bottom. So we get n choose k equals n factorial divided by k factorial times n minus k factorial. And if we want to do an example, say we have the set S that is all the integers from 1 to 8, and ask ourselves, well, how many subset of S have 5 elements, but also have 4 and 7 as a subset? So that means we have 5 elements in the set, 2 of those have to be 4 and 7. Well, I mean, there are 8 choose 5 subsets of cardinality 5. However, we're not going to want a lot of those, actually, right? A lot of them don't have 4, don't have 7, certainly don't have both, right? So we're going to have to count it in a more thoughtful way, right? So let's look at our subsets. Well, we know for sure that 2 of the elements in our subsets are going to be 4 and 7. So those are already taken up. So really, all we really want to do is fill in those last 3 spots. So how do we fill in those remaining spots? Well, we have 3 elements to place in our subset, but we don't have 8 elements to choose for them, right? Because we've already chosen 4 and 7. We can't choose 4 and 7 for those last 3 spots. So even though we had 8 choices in the beginning, once 4 and 7 are in there, we only have 6 choices left. So we have 6 elements to choose from. We have 3 spots to fill. So this is exactly like choosing a subset of 3 elements from a set of 6 elements, right? Our 6 elements are 1, 2, 3, 5, 6, 8, right? And we're choosing 3 elements from them. So that means we have 6 choose 3 subsets. All right, so now that you've seen how those go, I would encourage you, especially if you had some struggles in those in-class activities before, to go revisit those, right? So revisit the in-class activities that we did for the previous parts of this section and see if this video helps you understand them better.